All right, welcome. Today we are going to be reviewing radicals. So you're actually going to have to flip ahead pretty far in your note packet to page 28. So if you need to pause this video while you do that, go for it. Because everything in between where we left off and where we're going to be now, we haven't covered yet. So time will tell if and when we get to that. So let's just review radicals. There's a lot. We split radicals up at the time to simplifying radicals and graphing radicals. And we're going to do both of those right now. So fingers crossed. The first thing that we need to talk about in when we are introducing radicals is what makes a number irrational versus rational. So we could be looking at two different numbers, the square root of 4 and the square root of 5. One of those is considered rational, and the other one is considered irrational. Obviously, the square root of 4 is 2, so that is what we would consider our rational value. And the square root of 5 cannot be simplified, so that one is our irrational value. So the definition of rational is a number that can be expressed as a fraction, but a lot of people think of these as nice numbers. They don't have to be nice numbers. Like letter C, 0.468 is considered rational because there is a way that I could write that as a fraction. So one way you could check is by typing in, if it's a decimal, is by typing in 0.468 and then math frac. If your calculator, 0.468 math frac. If your calculator can, oh my gosh, turn that into a fraction, then it is rational. So some people think terminating, meaning a decimal that ends, so 0.468 ends, so terminating. A repeating decimal, so in letter B where we have 0.13131313, that would be considered rational because there must be a way for us to express that as a fraction somehow. And 3 2/7 already is written as a fraction, so that would be rational. But if you have a decimal that is non-repeat, and non-terminating, so it either has a ... and it has no rhyme or reason to its pattern that could be expressed as a fraction. So if it cannot be expressed as a fraction, we consider that an irrational value. Pi is one of the most famous irrational values. The square root of 36 is regular old 6, so that would make it rational. But if I type the square root of 26 in my calculator, okay, so if I do second square root of 26, enter, notice the decimal has no rhyme or reason or pattern to it, and if I math frac that, it cannot turn it into a fraction, so that would be irrational. -5 is a nice whole integer, so that would be rational. Then we moved on to simplifying radicals and operations of radicals and things of that nature. Square root of 81, everyone knows that's a nice 9. 49 is 7 and 9 is 3, so that gives me 21. 16 times 25 can be broken apart to be the square root of 16 times the square root of 25, so that'd be 4 times 5, which is 20. And if you have an exponent under a radical that is even exponents are considered perfect squares. So if we're taking the square root of something, this would be the square root of 64, square root of x squared, and the square root of y to the 6. So that would be all perfect squares. Same thing with letter E, so I'm going to skip that. But in letter F, this is where we might have to split it, and I, in my class, call it good versus bad. I put all my perfect squares in the good side, and all my non-perfect squares in the bad side. So 18, I have to find a perfect square that goes in evenly into that. So in my calculator, if I go to my y equals screen, if you're not confident in what your perfect squares are, just type x to the second power, go to your table of values, and every single thing in your y list is considered a perfect square. So look in your y values, those are all perfect squares. So if I list them out, I have 4, 9, 16, 25, 36, 49, 64, 81, 100, and the list would keep going on and on and on. Those are perfect squares. So 18, what I notice is 9 times 2 is 18. C to the first power, since that is not even, that's going to go in the bad side. D to the 4th power, it's even, so that's going to go on the good side. And e to the 5th has to split up to be e4 and e1. Now everything on the left radical is a perfect square, so this would be 3d squared e squared, and then the 2ce is going to remain inside its square root. So let's practice that one more time. Let's take a look at letter H, because this one has a coefficient. So, negative 2x squared y is our coefficient. Now let's break apart 27. So 27 is not on my list that I wrote at the top of my page. I need to find a perfect square that goes into it. And the perfect square again is going to be 9, but this time 9 times 3. X to the 7 is not even, so I break it up to be x6 and x1. And then same thing with y9, it's going to be y8 and y1. Then I apply the radical to the first square root. So everything else just kind of gets rewritten. Nothing changes in everything else. But in that middle radical, that middle thing, it's going to be turned into a 3x cubed y4. I just literally took the square root of everything in that first radical. Now what's happening between our coefficient and our simplification there is multiplication. So negative 2 times 3 is negative 6. X squared and x3 give me x5. y1 and y4 give me y5. And then we have a square root of 3xy left. The regents, nor me or Miss there, are going to ask you the 4th root or the 5th root of something. But we might ask you the cube root of something. Perfect cubes are a different type of animal. So let's take a look at letter J. So if typing in x squared in our calculator got us our perfect squares, then x raised to the 3rd power should give us our perfect cubes. So as I scroll back upwards, 1 is a perfect cube, 8, 27, 64, 125, and I probably won't go much higher than that. So our perfect cubes are 1, 8, 27, 64, and 125. Now, what's interesting is you can't take the square root of a negative. So if I tried to take the square root of a negative 4, my calculator actually would say that there's an error with that. It's not real. But if I do math option 4, and I take the cube root of negative 8, I actually can. So the reason why I'm bringing this up is all of my perfect cubes can actually be positive or negative. All of these would have a big plus or minus in front of it because positive 8 and negative 8 are considered perfect cubes. So in letter J, since 16 is not on my perfect cube list, I'm going to break this up to be a good perfect cube and a bad perfect cube. Negative 16 is going to get broken up to be negative 8, that's the perfect cube, times 2, which is the non-perfect cube. X to the 2nd power, because now that we're dealing with cubes, it's not big enough to be considered a perfect cube if there's only 2 x's. So that goes in the bad side. But y cubed is going to go in the good side, because there's 3 of them. Z8 is going to have to break up, but this time not even versus odd, it's going to be power of 6, or powers of 3, I should say, multiples of 3, and then whatever your leftovers are. Oops, wrong letter. Sorry, it should be a Z. Z squared. So now everything on your left radical should be a perfect cube. So the cube root of negative 8, you could type it in your calculator if you didn't know. Y cubed, and then I take the cube root of that as just y. Z to the 6th power, taking the cube root, would be z squared. And then this is just going to get rewritten because I can't reduce it any farther, and that's your final. All right, moving on to adding and subtracting. So to add and subtract, the only way you can add things if it looked like this is if they were all the same letter, and then I could put them together. It's the same way. As long as my radicals match, I can put them together. So I would just do 4 minus 8 plus 3 4 minus 8 is negative 4. Negative 4 plus 3 is negative 1 radical 5, and that's my final answer. This 2 is the same exact thing as it would mean for if these were x's. I write it 2 times, and I would FOIL it out, but I'm not going to do that one. I'm going to do just letter C, I think. So if I distribute this out, no, maybe I will do this one. It probably looks the scariest to you guys, so I should probably do the scary looking ones. All right, so 2 radical 3 times 2 radical 3 is 4 radical 9. Then I go take the 2 radical 3 and I go all the way out here. So 2 radical 3 times 3 radical 2 is going to be a minus 6 square root of 6. Now I'm going to do the 2 inside ones. So negative 3 radical 2 times 2 radical 3 is going to give me another negative 6 outside and then a radical 6 on the inside. And then last but not least, negative 3 times negative 3 is a positive 9. Radical 2 and radical 2 give me radical 4. Now there's definitely some cleaning up that I can do here because I noticed some perfect squares. 9 is a perfect square and 4 is a perfect square. So over here I have 4 times 3. Over here I have 9 times 2. And in the middle I can combine like terms, just like we talked about on letter A, so minus 12 radical 6. So let me bleed into this next question. So 4 times 3 is 12 minus 12 radical 6, and then 9 times 2 is plus 18, and you can only put like terms together, so 30 minus 12 radical 6. Done, done, done. Don't put those together. Do not do 30 minus 12. They are not like things. All right. This one's actually pretty easy because if I can just if I can split up multiplication like I did at the top of the page, then there is no reason why I can't just divide these. So I should be able to just write this under one big radical, use my exponent rules to simplify that. 3 goes into 75 25 times. X cubed divided by x would give me x squared, and my y's cancel each other out, and then that problem became something very simple as opposed to having to do anything else. You would do the same thing on letter H. So divide your coefficients, which would be 5. Divide your radicands. So this is 4 goes into 32 8 times. Look at your A's. There'd be 4 left. Look at your B's. There'd be 1 left. And then you always want to put your answer in simplest radical form. So if that wasn't a perfect square, then you reduce it farther. So 4 times 2 is 8. A4 is your perfect, and B goes in the bad side because there's only one of those. And then multiply your coefficients together. All right, we are making good time. We did something like that. Okay, letter J is something called rationalizing. And the reason why we have to rationalize is when we end our final answer, if our final answer has a radical in the denominator, in the bottom, we can't leave our answer like that. So what we learned was we multiply the top and bottom by the radical that's in the bottom. So that would be create a radical 3 on top and a square root of 9 on the bottom, and that is like magic. It gets rid of the radical that's in the denominator. All this really is equivalent to is 1. It's like a magic 1, because anything divided by itself is 1. I just kind of manipulate the way that the answer looks. We should do L and M, and then we're going to move on to graphing. Actually, we probably don't have to because we did one the other day. So we actually probably can skip those and move on to the last page. So let's do letter L and M, and then we'll skip to that last page there. So I can't add these the way that they are. They are not like radicals. So that tells me that I'm going to have to do a lot of splitting. I'm going to have to get my perfect square list back out and see which ones, what the largest perfect square that goes into all these numbers are. So 49, or 98, the largest perfect square is 49 2 times. 8's easy, that's just 4 times 2. Remember, you always put the perfect square on the left. 128 might take you a minute because, again, you want to pick the largest perfect square, not just any perfect square, and the largest perfect square that goes into it is 64 2 times. Now, if I am going to be asking you to add or subtract, remember we have to get like radicals, so that should be a pretty good indication that all of our radicals and our bad side should match. So maybe that's a little hint for you. I should say should. I can't say always will, but they should. Oh, sorry, that's my dog. Probably heard another dog barking. So I took the square root of 49, I took the square root of 4, I took the square root of 64, and now I can find my coefficients and add them up. 14 minus 2 is 12, and 12 plus 32 is 44 radical 2's. That's your final. We did something similar like letter M the other day with x's. I would set this one up the exact same way, and I would just separate them and turn them into 2 separate terms. And then I can reduce this super easy because the 6's cancel each other out, and 4 goes into 12 3 times. The 4's cancel each other out, and 6 goes into 12 radical 2 times. So whatever's out of the radical stays an integer, and whatever's under the radical stays under the radical. I'm going to skip A and B because we graphed square roots and cube roots just the other day. And then the last thing I need to talk about is power over root. So when you have something raised to a fractional exponent, I always think power over root. So if I have 15 to the 1/3, 1 is your power, and the 3 is your root. So if I want to rewrite 15 as a radical, it would be 15 to the first power, and then I take the cubed root of it. In letter B, k is the only thing being raised to the 1/2 power, so k would be raised to the first power, and then the square root would go only around the k. The 4 technically is like being multiplied. It's just multiplying that result. But in letter C, all of this is being raised to the 1/3, so all of this is being raised to the first power, and I'm taking the cube root of all of it. If I want to go in the opposite direction, remember, if you raise something to the first power, you really actually don't have to write the 1 if you don't want to. So in letter D, this is technically 40 to the first power, and I'm taking the second root of it. So that's the same thing as 40 to the 1/2. Those are interchangeable. They're equivalent. So same thing with letter E. This is 16 to the first power, and I'm taking the fourth root of it. So that would be how I could write it as a fraction. And 5 to the second power, and I'm taking the cubed root of it. So if you want to play around with the bottom equations, but because none of them until you get to letter K have a variable in it, you literally can just type them all in your calculator. You would just type 3125, remember power over root, you would type that in your calculator and it will actually give you a value. The answer is 5. So yeah, you could literally just type all these in. The ones that you can't just type in is letter K whenever there's variables in it. So this is where we're going to have to combine some of our thought processes together. We've learned that a negative flips things. So this would be 1 over k to the 1/2. And then we just learned on the top of this page that something raised to the 1/2 power is the same thing as taking the power over root. So this would be the same thing as 1 over the square root of k. And if you wanted to rationalize that and practice what we did on the last page, that's cool too. But so just kind of combining some of the things that we've reviewed. All right, well, until next time.